Hello, my name is Oren, and today I'm happy to present our work on a new image codec that is specifically optimized to yield high perceptual quality, but at the same time contains all the pieces for practical deployment. Over the last few years, learned image codecs have overcome many obstacles that had previously blocked practicality, including computational efficiency and robust interoperability across devices. With that said, none of the practical learned codecs has been optimized for perceptual quality, which is quite challenging to do under stringent compute constraints. In our work, we aim to bridge this gap by introducing the first codec that is both perceptual and practical. It is fast and comes with cross-device guarantees. As can be seen in the table on the right, it achieves 2.3 to 3 times bitrate savings over existing standards such as HEEC, AV1, and VVC, and even future ones such as AV2 and ECM. It also achieves 20 to 40% bitrate savings over the best learned perceptual codecs. At the same time, the codec runs at practical speeds and can run on an iPhone 17 faster than most state-of-the-art ML codecs run on a V100 GPU. Given that the codec is perceptual in nature, to measure the bitrate savings, we ran large-scale subjective studies based on standardized and rigorous methodology and received 75,000 user ratings. Out of those, we generated Bayesian ELO curves based on real human opinions of image fidelity. Looking at horizontal slices in the graph, you can see that Pico, with the curve at the top left, requires significantly lower bit rates to achieve the same quality level as evaluated by humans. Looking at vertical slices, it can be seen that for the same number of bits per pixel, Pico achieves considerably higher perceptual quality. To derive the codec, we combined contributions from 3 different areas: enhancements to the overall architecture of the model, a large-scale neural architecture search, and finally improvements to the perceptual training recipe. Let's briefly dive into some of these. For the architectural improvements, we introduced several different tools that we found helpful for learned image compression. For example, we explicitly learn the quantization width, and we signal it within the hyperlatent in addition to the location and scale. And we introduce what we call a one-shot context model, which iteratively refines the location and quantization width. The key observation here is that because the module is not touching the scale, it doesn't actually require iterative entropy decoding and can be all ran contiguously on the ML accelerator. We then ran a large-scale neural architecture search over the different hyperparameters in the model. For the decoder, for example, we started with 1.4 million configuration candidates and gradually narrowed them down, first based on Kmax per pixel filtering, which is very cheap, and then measuring actual on-device runtimes, and finally training to completion a subset of the models which achieved the runtime target. In this example comparison, you can see the various improvements in play. It can be seen that Pico provides considerably improved detail preservation over HEEC, which is a state-of-the-art codec. This example is not cherry-picked, and similar improvement can be seen more generally, and across other existing and future standards. That was our compressed summary of our compression paper. We invite you to read the paper to learn about all the fine details and look at our project page for a demo of the codec. Thanks very much.